Circular and elliptical motion. Let the position vector of a moving particle p at time t be r is equal to a sine omega t plus pi plus b cos omega t plus q j. Since I like column vectors, I would clearly write this as a sine omega t plus p and b cos omega t plus q. That gives us, when we differentiate, that the velocity is a omega, don't forget to use the chain rule there, cos omega t I, take away b omega sine omega t j. And the acceleration, differentiating again, would be negative a omega squared, again use the chain rule, sine omega t I, take away b omega squared cos omega t j. So as column vectors, our velocity is a omega cos omega t and negative b omega sine omega t, and then the acceleration is negative a omega squared sine omega t and negative b omega squared cos omega t. We can then form the Cartesian equation by eliminating t. So working from here, we have x is equal to a sine omega t plus p, y is equal to b cos omega t plus q, and rearrange, we've got sine omega t is x minus p over a, cos omega t is y minus q over b, and then since we know that sine squared omega t plus cos squared omega t is 1, if we have x minus p over a squared plus y minus q over b squared, we know that must be equal to 1. And we can write that as x minus p squared over a squared plus y minus q squared over b squared is equal to 1. And if you plot that, it's going to look like this. It's an ellipse. We can see the center of the motion is p and q, which were the constants here and here, so that identifies the center of the motion. The major axis we can see has a length of a. The minor axis is b, and think about where those came from. So we've got a here and b here. And at t equals 0, if we go up here, sine of 0 is 0, so that would just be p. Cos of 0 is 1, so we'd have b plus q, or q plus b. And you can see that's where it is at t equals 0. And then you can check as you change the value of t which way round it's going to go, and it goes in this direction as indicated. So it start at this point up here and go clockwise in this case. If a is not equal to b, then the path is elliptical. If a is equal to b, the path is circular. We talked about the lengths of the major and minor axes, and if both of them are a, then they'll be the same and it will go in a circle. Here's an example. I've got r is equal to 2 sine omega t plus 1, 3 cos omega t plus 2, and you can see that the center of the motion here is at 1, 2. We can see this axis has a length of 2 and this one has a length of 3. We can see in this case it is going clockwise and it starts at the top here. If instead the position vector is given by r is equal to a cos omega t plus p and b sine omega t plus q, then when omega t is 0, r is at a plus pq. If omega t is pi by 2, you can just substitute these in. R is equal to p b plus q. Remember, sine of omega t is 0 if omega t is 0. Sine of 0 is 0, that's what I mean. And we know the cosine of pi by 2 is 0, and the sine of pi by 2 is 1. That's how we're getting these. Omega t is pi. R is equal to p minus a over q. If omega t is 3 pi by 2, r is going to be p q minus b. And omega t is 2 pi, r is a plus p over q. You could go back through those if you want to and just give it a check using the standard values that you know, as I've mentioned. And then it would look like this. And we would have at t equals 0, it would be over here, so this would be the start point, and this time it would go anti-clockwise around the ellipse.